Cooling towers are crucial for reducing chiller kW consumption, acting as the exit point for all BTUs in a chilled water system. The refrigeration cycle involving water-to-water chiller and cooling towers transfers heat from the building to the atmosphere using 4 main components. The compressor takes low-pressure, low-temperature gaseous refrigerant and pumps it to a high-pressure, high-temperature state. The condenser then cools and condenses the hot gas into a liquid by exchanging heat with the cooling tower loop. An expansion device reduces the liquid's pressure, cooling it to a cold liquid state. Finally, the evaporator absorbs heat from the chilled water, causing the refrigerant to evaporate, restarting the cycle. A nominal ton for a cooling tower is defined as 3 GPM of water cooled from 95 degree F to 85 degree F at 78 degree F wet bulb. A nominal cooling tower ton is 15,000 BTU per hour. An evaporator ton, refrigeration ton, is 12,000 BTU per hour. The difference accounts for the 3,000 BTU per hour of heat generated by the compressor in a typical air conditioning application, which the cooling tower must dissipate. The CTI rates all cooling towers based on the following standard design conditions: temperatures, 95 degree F, 85 degree F, 78 degree F wet bulb, range and approach, 10 degree F range, and 7 degree F approach. Flow rate, 3 GPM per cooling tower ton. These are standard rating parameters and should not be used as the design conditions for a specific application. The design must use the actual design wet bulb conditions for the region. Cooling towers can be designed to operate at ranges higher or lower than the CTI-rated 10 degree F. Changing the range impacts both pump and chiller energy consumption. When you increase the range, for example, from 10 degrees to 15 degrees, you're removing the same heat load with a larger temperature drop. That means you need less water flow, dropping from roughly 3 gallons per minute per ton to about 2. Lower flow reduces pump horsepower and saves pumping energy. However, there's a trade-off. A higher range raises the average condenser water temperature. That forces the chiller to work harder, which increases compressor power. The approach temperature also affects the initial cost and size of the cooling tower. Higher approach results in a smaller cooling tower, lower first cost. Lower approach results in a larger cooling tower, higher first cost. Cooling towers operate on evaporative cooling with counterflow and crossflow configurations. Counterflow towers pull air up while water sprays down, creating an opposite flow. Air is drawn upward from the bottom through the fill and exhausted at the top. At the same time, condenser water is sprayed downward through pressurized nozzles. Because the air and water streams interact vertically, these towers typically have a smaller footprint. One trade-off is pumping energy. The spray nozzles require additional pressure, which usually adds 3 to 6 psi of head on the condenser pump. Crossflow towers are arranged differently. Air is pulled in horizontally through louvers, moves across the fill, then rises through an open plenum in the center to exit. Meanwhile, hot water enters shallow basins at the top and flows straight down through drilled openings, relying solely on gravity instead of spray nozzles. With air traveling perpendicular to the falling water, crossflow towers tend to require more space to accommodate the central air pathway. That same open center makes access easier, resulting in a more maintenance-friendly design. The wet bulb temperature is the critical factor that determines how effective a cooling tower will be at releasing heat into the atmosphere. The wet bulb temperature is the lowest temperature that can be reached under the current ambient conditions by the evaporation of water. It is determined by the actual air temperature, dry bulb, and the humidity, amount of moisture in the air. A higher wet bulb means the air is already saturated, like a damp sponge, making it harder to evaporate water and requiring the cooling tower to work harder to maintain set points. Conversely, in arid regions with a lower wet bulb, like a dry sponge, evaporation occurs quickly and thoroughly. Let's start with what happens when a cooling tower is overflowed. When the entering water exceeds the tower's maximum flow rating, proper distribution across the fill is lost. The hot water basin can flood, spilling water and wasting expensive treatment chemicals. This overflow also wastes pump and fan energy, and in cold conditions, the spilled water can freeze, creating a safety hazard and potential damage. Underflowing is equally problematic and can be even more harmful. Too little flow through the tower reduces wetting of the fill, leading to what's known as dry air disease. As supply temperatures rise, the tower fans speed up in an attempt to increase evaporation. But without enough water, sections of the fill dry out. Air then moves through these dry, low-resistance paths, bypassing the wetted areas. Mineral deposits form on the dry surfaces, creating scale that reduces heat transfer and forces the fans to work harder. The result is wasted energy and long-term degradation of tower performance. ASHRAE 90.1 code suggests a 50% turndown for new installations to allow substantial flow reduction. Weir dams are recommended for existing towers to ensure fill surfaces remain wet during low flow. Constant condenser flow is advocated by most chiller manufacturers to keep tubes clean and prevent scale. Increasing range reduces GPM and pump horsepower, but raises chiller kW due to higher condensing water temperature. A higher approach allows for a smaller cooling tower, resulting in a lower first cost. Cycles of concentration. Compare dissolved solids in recirculating water versus makeup water, controlled by blowdown. Successful cooling tower operation requires a balance between preventing scale and corrosion from dissolved solids and conserving makeup water. This balance is achieved by controlling the cycles of concentration, COC. ASHRAE 189.1 requires 5 cycles for makeup water with less than 200 ppm hardness and 3.5 cycles for more than 200 ppm hardness. The required minimum COC is based on the makeup water's total hardness, calcium carbonation. Building codes and standards, such as Standard 189.1 for the design of high-performance green buildings, regulate cooling tower water consumption and require specific equipment and performance thresholds. Required equipment: makeup and blowdown meters, conductivity controllers, overflow alarms. The standard also includes provisions for water efficiency elsewhere in the cooling system, such as requiring the recovery of condensate from air conditioning units with a capacity greater than $65,000 BTH 19 kDor for reuse. Cooling towers must be equipped with efficient drift eliminators to reduce drift to a maximum of 0.002% of recirculated water volume for counterflow towers, 0.005% of recirculated water volume for crossflow towers. Good suction piping design protects the condenser water pump by preventing air pockets and cavitation. Cooling tower water carries air, and if pressure drops too quickly, that air can separate and enter the pump, damaging the shaft. If pressure drops even further, water can flash to vapor and cause cavitation. To avoid this, use eccentric reducers with the flat side on top so air can't collect. Keep the suction piping straight and free of unnecessary fittings. Place valves and strainers on the discharge side, not the suction side. Limit pressure drop between the tower and pump suction to about 5 feet. Use a compound gauge on the pump suction to read both positive and negative pressures. Slightly negative readings at startup are normal. On the discharge side, the goal is to keep the tower from flooding when the pump stops. Route horizontal discharge piping below the tower overflow, or install a water leg to trap water. Use a non-slam check valve to prevent backflow. Size the discharge piping per ASHRAE 90.1 guidance, and include 5 to 10 feet of extra head for fouling in open cooling tower systems. There are 3 main piping arrangements for chiller and cooling tower systems. Option 1 is the independent circuit. Each chiller has its own pump, cooling tower, and piping. There's no common header, which keeps control simple since each circuit can be turned on or off independently. However, flexibility is poor. There's no standby capacity. If a tower fails, that circuit goes down. Because of the duplicated piping, this option is typically the most expensive and is rarely used. Option 2 is header, supply, and return. Here, each chiller still has its own pump, but the supply and return are tied together in a shared manifold. This reduces piping cost and allows any chiller to operate with any tower. With added butterfly valves, you can even create pump and condenser standby. However, at part load, friction losses in the common pipe drop. The highest head pump can run off its curve and overflow a chiller, potentially damaging its tubes. To manage this risk, designers either select pumps with safe head limits or install flow limiters on the chillers. Option 3 is parallel pumping. In this arrangement, all pumps connect to a single supply header feeding every condenser and a single return header from the towers. This provides maximum flexibility. Any pump can serve any chiller or tower, delivering strong redundancy. The trade-off is risk. Because all pump flow enters a shared header, the chance of overflowing a condenser is even higher than in option 2. To protect equipment, flow limiters are highly recommended, and off chillers should be isolated using two-way valves. Using identical pumps also simplifies control. Mitigation includes installing flow limiters on chillers and using two-way valves to prevent flow when chillers are off. The design engineer creates the staging sequence, ensuring flow remains within the tower's minimum and maximum limits for all equipment. Cooling towers need unobstructed space to prevent warm, moist air recirculation. The fan discharge cylinder must be level with or higher than any adjacent walls near the clearance boundary. Poor clearance leads to elevated wet bulb temperatures, reduced capacity, and increased energy consumption. Understanding these principles is vital for efficient cooling tower operation and overall HVAC system performance.